Alrighty, here's the number 4. I think this is going to get its own video, this page. So we got a bungee jumper who's jumping off a bridge. And this whole distance is 40 meters. And here's the bridge, there's the ground. And this point right here at 10 meters down is important because that's where the cord starts to stretch, right? The cord's 10 meters long. So for the first 10 meters, she's just falling. The cord's not stretching yet, and then it starts to stretch. So we're going to do, this is going to be our position A, our position B for part A. All right. So if that's position A and that's position B for this part, then here, this is going to be my height 0 for this first part. I'm going to have to reset that when she falls past that. But for right now, for these two, position A and position B, this is the lowest. So that's how we're going to do it. So just for there, while she's just free falling, then we're going to have EG, turn it into EK. Why no EG here? Because this is the lowest she gets for these two positions. So I'm just going to make that height 0. So here, what do we need in the system? We need the jumper, and we need the entire Earth. If you put the bungee cord in there, sure, you can put it in there. It doesn't actually matter for this one because it's not stretching yet. How fast is the jumper falling after she's fallen 10 meters? So that means we want to write this equation. EG is equal to EK. And that's 10 mh equals 1/2 mv squared. So you can plug everything in. If you notice right here, the m's cancel out, whatever. So do some math. Let's see, she's 65 kilograms. Our height is 10 equals 1/2 times mass. And we're trying to figure out how fast she's going. Do the math. Be careful. You know how to do algebra. Should get about 14 meters per second. All right, so now position A is 10 meters below the bridge, and position B is at the bottom of the fall, not at the ground, at the bottom of the fall. So how far does she fall? I don't know. And we don't know actually if the bungee cord's good enough to stop her from hitting the ground. So there's kind of we don't know how far she's going to fall. But for part C, this is my new position A. And my new position B is wherever the bottom is here, however far down she goes. And we don't know what that is. So we'll just kind of imagine that the ground is not there for the purpose of making this calculation. So what's she got at the top? At the top, she's got some EG, although I don't know exactly how high she is. So I wouldn't be able to put a number on this yet. And then at the bottom, the very bottom, she's got all... Oh, wait a minute. Let me back up here. Messed that up, didn't I? Because this is not where she's jumping from. So she's got, when she gets to here, she's going 14 meters per second. So she's got EK. Oops, let me get my pen back. She's got EK and she's got EG, right? She's got this much worth of EK. And then here, she's got all EE because she's at the lowest point. And because it's the lowest point, so she's stopped and there's no EG anymore because this is our height 0. All right, so now it's the same. We need the jumper and we need the entire Earth, but we also need the bungee cord in here because it's going to be stretching, giving us the EE. So write the equation for that. That's EK equals EG. Oops, sorry, that's plus. Those are on the same side. Equals EE. And we'll plug some numbers in here in part E. So write the quantitative conservation of energy equation and then figure out if she hits the ground. So let's see what we got here. So EK, that's 1/2 mv squared plus, I keep writing an equal sign there, plus 10 mh. And what h is this exactly here? This is the h that is like this unknown height. We don't know how far she's going to fall from here. Hopefully for her it's less than 30 meters, but we don't know. So that is an unknown h, and that's equal to 1/2 kx squared. And then what's the x? How far is the bungee cord stretched? Well, it starts stretching right here. So however far she falls here, that's the same as the x, how much it's getting stretched. So I think we have to realize here that this h and this x are the same thing. That's how far she's fallen, and that's how far it's stretched. And since we reset here, position A, to be where the cord starts to stretch, that's why we did it this way. All right, so I'm going to put some numbers in. 1/2 mv squared plus 10 mh is equal to 1/2 k, was the k, 30 times, and then instead of writing an x here, I'm going to write an h squared, since those are the same. You could have made them both x's either way. Now that is an equation that has an h and an h squared, so we need to solve that by graphing. What I did here for graphing is I left this expression and this expression, and then I subtracted this over to the other side. And then I graphed that. You got to mess with the window, because it turns out when you solve that with your calculator that the h is equal to about 52 meters. And what does that mean? Well, she only had 30 meters to go to the ground. So if the h is 52, she's going to hit. She's probably going to hit pretty hard. Yikes. So make sure you can do that in your calculator, graph that, and there you go. There's number 4.